Okay, let's do the post-processing and let's calculate the stresses now. Now, stress in an element is equal to its Young modulus multiplied by its strain. Okay, and the strain is the basically the elongation divided by its original length, LE. Now, the elongation is due to the differences in displacement values at two ends of an element. Therefore, we can easily say that for an element, it is the node 2 of the element minus node 1 of the element, the displacement of node 2 and minus displacement of node 1 of an element. In fact, for two-dimensional case, we can write it like this. So Young modulus divided by the length minus 1, 0, 1, 0. It is just an identical way of, it's the same equation actually, but just we use matrix vector notation in order to do this operation. So this is minus 1, 0, 1, 0 multiplied by the root. So these are the element wise in the element coordinate system. In order to transform it into the global system, we have to multiply it with the rotation matrix, right? So the rotation matrix multiplied by the displacement in the global system will give us minus 1, 0, 1, 0. And in fact, this is nothing more than this one for the first element, because the displacements for the first element is 0, 0, 10 plus 20 square root of 2 minus 10. We have only displacement values in node 3, and node 1 and node 2 have 0 displacement. Okay, then the stress is equal to 0 minus 1, 0, 1, 0, 0, 10 plus square root of 2 and minus 10, and divided by 1 over A, because the Young moduluses, so we have A multiplied by E here, and we have another E here, so these Young modulus values will cancel each other, and as a result we are left with this value. Okay, for the stress in element 1. For the stress in element 2, it is the global stiffness value, so these are the nodal displacements at node 2 in x and y direction, they are 0, and this is the nodal displacements at node 3, and then we multiply it with this vector. This comes from the stiffness length, this square root comes from the length, and as a result we obtain the stress for the element 2 as 10 square root of 2 divided by area. Okay, how about the three-dimensional problems, three-dimensional truss systems? So remember that this is a one-dimensional relationship between the forces and nodal displacements in an element for one-dimensional system. Now, of course, we may have three-dimensional truss system. In this case, we do the same thing that we did in two-dimensional problem. So we put u1x, u1y, u1z for the first three members of the vector, and then u2x, u2y, and uz. So certainly we group the nodal values into due to the nodal displacements in each direction for the first node in the first three elements. Then we do the same thing for the second node, and in fact we do the same thing for the force vector. But now we have a director vector or unit vector along the truss element. We need to define it. In this case, what we do is we calculate the relative position of node 2 with respect to relative position of 1. We know it from statics. So first we calculate the x21, then we calculate the y21, then we calculate the z21. So these are the relative positions of node 2 with respect to node 1 in each direction, and then we divide it with the length of the element. This gives us the unit vector from the first node to the second node, okay, in the direction of the truss system. Then we obtain the rotation matrix, which is a 6 by 2 matrix. Why we have 6 by 2? Because we have 6 elements. Sorry, the transpose of the rotation matrix is 6 by 2, and the rotation matrix itself is 2 by 6. Because we can write the displacement then along the truss element u1 prime x I prime u1 prime 1y j prime u1 prime 1z. Okay, so this is the displacement in the element coordinate system, I1 prime, and k. Okay, so j prime and k prime are orthogonal to the I prime, or orthogonal to the truss axis. Then this has to be equal to this vector, okay, u1xe, u1yc, u1ye and u1ze k in the global. This is the displacement vector at a node in the global coordinate system. Now we can write it like this. So u1 prime x is equal to u prime u, this is the displacement vector, multiplied by the I prime, and this gives us this vector, and in fact this is what we are going to obtain then. This is the rotation matrix x21 y21 z21 0 0 0 0, and then again x21 y21 and z21. This is the displacement in the global coordinate system. This has to be divided by the length of the element. This is, then the rest is not that different than the two-dimensional problem. Okay, thank you.